Now in this lecture we will introduce the concept of electrostatic potential energy and the electrostatic potential. Now we know that the force on a charge in the field is given by F is equal to Q E. Now if we put some external work to move this charge against the field such that the kinetic energy does not change of this charge, that is very slowly, quasi-statically, we move this charge against the field. So the work done which we will do will be stored as a potential energy inside it, inside the field, electrostatic energy. Okay, so this is the work done when we will be going from position 1 to 2, and this will be equal to the delta W, work done against the electric force. Okay, now the work done per unit charge is called the potential, electric potential. So it implies what we have, delta W over Q is equal to minus E dot dl from position 1 to 2 is simply work by Q minus at position 2 work by Q at position 1. So this work done per unit charge is known as potential and represented as phi over V. So this is the definition of the electrostatic potential. So from point 1 to 2 we are taking the charge, that is, this is point 1, this is point 2, and this charge Q is moved from 1 to 2, and field, let us say, is in this direction like this. So what we are doing work, let us say this charge is positive and field is in this direction, so the force will be in this direction, the electric force. So we are going to do work against this electric force while taking from this charge from point 1 to 2. So this work done will be stored in the electrostatic as the electrostatic potential energy. So the electrostatic potential energy at 2 will be higher than 1 in this case when this field is in this direction and we are moving in this direction and the charge is positive. Okay, so this is the potential at 2. Since we have defined work done per unit charge as potential, so this Q will not come in the denominator. Phi2 minus phi1 or V2 minus V1 is equal to minus E dot dl 1 to 2. So this is the relation which we are going to use for the electrostatic potential difference. Okay, now what happens if this point 1 to is same? Let us say we make a completely closed loop, so it will be V2 minus V2 equals to 0, and this is closed loop. So you see, as we have already seen earlier also, that this electric field is conservative in nature, that is this closed loop line integral is 0, or we can say that del cross E is equal to 0 using Stokes theorem only. It implies we can represent it as a gradient of a scalar quantity. So, and this scalar quantity is the potential. Now we will see how we will use the electrostatic potential to find the electric field. Now this was defined for let us say one charge. This field was created by, let us say, one charge. What if there are so many other charges? So what was that? This phi 2 minus phi 1 was minus E is nothing q by 4 pi epsilon naught r square, and this is dr. and this is direction AR from 1 to 2. So if this point charge Q is considered as at the origin, so it will create field radially, so electric field will be in the direction of AR only, and direction of movement is, let us say, DR only. So this is what we are trying to show here. So this is the electrostatic potential due to one charge. What if there is so many charge? Let us say it is just a volume charge distribution. So this Q will be replaced by rho dV dash over a volume V dash. This sphere is having volume V dash. This prime or dash is shown to be source point. That is, this integral is going to be done over the source points, not the field point. So potential at 2 minus potential at 1 is simply given by rho dV over 4 pi epsilon naught r square AR dot dr, and this integration is over V dash, and this is from point 1 to 2 and minus sign. Okay, so in this way we can see that potential is also following the principle of superposition. That is, potential at point 1 is because of, let us say, so many charges Q1, Q2, Q3. So we can find the potential at this point 1 because of many charges just by finding the potential separately and then adding them. So this potential is also following the principle of superposition. Okay, now let us try to find the formula of the electrostatic potential if we consider that this reference point is at infinity. So we have seen previously in this slide that we are always writing phi2 minus phi1 as minus, let us say I am just assuming a point charge q by 4 to generate the electric field 4 pi r square dr from point 1 to 2. So I will solve this integral. It will give me q by 4 pi epsilon naught 1 by r2 minus 1 by r1. Let us say this r1 is at infinity. So what will happen to the definition? Now what I will assume that phi at infinity, that is r1, that is phi 1 is equal to 0. It implies phi 2 minus phi 1 is equal to phi 2 1 is equal to phi 2 is equal to phi 2, because this is equal to 0. We have assumed by convention that infinity the potential is taken to be 0, and by this relation, if r1 is taken to be infinity, this term goes to 0, and this is just r2 or r. Instead of writing it r2, I will just write it as r. So potential at any general point r from infinity is q by 4 pi epsilon naught 1 by r. So you see that if I take this origin, and at infinity, this is, let us say, infinity, potential is taken as 0, or this is grounded. So at any point which is at distance r from the origin, the potential can be just found out by calculating the work done by taking a unit positive charge from infinity to here. So the work done per unit charge will be this potential of this point at r from the origin. Okay, since we are measuring these points with respect to origin while putting in this integral. So in this way we can calculate the potential of a point when we have assumed by our convention that infinity will serve the purpose of our reference potential. Now let us try to find the relation between this potential and the gradient. Let us take an example where this charge is moved in just x direction and it is fixed in the y direction and z direction. That is x to x plus delta x it is taken, and y does not change and z does not change. Okay, so the work done will be simply the potential at x plus delta x minus the potential at x. So this will be the work done against the electric field, or it is simply minus E x dx. Okay, taken from x to x plus delta x, work done per unit charge. Okay, now this phi x plus delta x minus phi x is equal to minus ex dx will give you, when I integrate from x to x plus delta x as, and we am assuming that e remains quite same because this delta x very small, so minus ex delta x approximately equal, because I am assuming that e does not change when I move from x to x plus delta x, is equal to phi x plus delta x minus phi x. So you see that ex minus ex is simply phi x plus delta x minus phi x over delta x, and this is approximately equal to, because still I am assuming that this delta x is still finite, but when I take the limit that this delta x goes to 0, this approximate sign will convert to equal sign, and we can find that ex is nothing but equal to minus dou by dou x of this phi. So similarly I can find for ey and ez equal to minus dou by dou z of phi, and for ey dou by dou y of phi. So you see E is simply minus of gradient of phi. So this is the relation which we already assumed by seeing that this electric field is curl free, electric field is curl free. But again we have proved that this is the relation which exists between the electric field and the potential of the point. Now let us find an expression of electric field when we know the potential. So as we have seen that potential at any point r due to the point charge is q by 4 pi epsilon naught r. This integral sign is not there. Okay. However, if this charge q is composed of, let us say, a volume charge, so to find this q I will replace it as this integral, that is I will find the total charge 4 pi epsilon naught r. So you see that this integral is with respect to the source points, not the field point, or this distance will again change, of course. This distance is between the source and the field. Okay, so you see that we can calculate potential at any point by any kind of charge distribution if I can calculate this integral. Now if let us say this is surface charge density, so what will I do? Sigma s ds dash over a surface of the total charge carrying surface over 4 pi epsilon naught r. So in this way I can calculate the potential, and this where we assume that phi at infinity is equal to 0. It is assumed. That's why I am able to absolutely say this is the phi at r. Okay, so this is the relation. Now using E is equal to minus del V. So what I will do, it is equal to E is equal to minus of del V rho dV dash over 4 pi epsilon naught R. This is V. So I will take its differential, or sorry, gradient. Now this integral is with respect to the source point, and this gradient is with respect to the field point. So these can commutate, means this can be kept brought inside the integral. So what is this? Minus rho dv dash 4 pi epsilon naught gradient of 1 by r. So this again we have calculated in one of the previous lectures. It is nothing, simply minus ar by r square, where this is the unit vector from r1 to 2, if this is r12, okay, from source to field point. So this comes out to be, minus sign will get cancelled when I put this value. So rho dv dash 4 pi epsilon naught r square a r. So this is the expression for electric field which we already know. Okay, so in this way we have completed the full circle and derived the electric field from the potential. Now what is the benefit of finding the electric potential instead of electric field first? The benefit is that this is a scalar quantity, so we have to just find one quantity only. However, if we are trying to find the electric field directly, we need to find the x component of the electric field, y as well as the z component. But for the v or the potential phi, both I use interchangeably. So I need just one number or one calculation, and once I found this, I can easily find the field by just using this. So this is the beauty of solving this problem using potential, the concept. Now let us try to see some relation between electric field lines and the equipotential surfaces. Now as you know that E is equal to minus del V. Now I have told you that the direction of gradient gives you the maximum rate of change. Of the scalar quantity. So this direction of E is in the direction of the gradient, or the opposite direction of the gradient. And this gradient is going to give you the maximum rate of change of this potential. So what it means that this is the equipotential surface where potential is not changing. So maximum change will be perpendicular to it. Otherwise, if there is it is not perpendicular, it is at some angle. So the same thing will not have the same effect. Like there will be a component here, and it will force to create a field in this direction. Okay, so we see that the electric field direction, which is the direction of the gradient, or the opposite, means because of this negative sign of the V. So this is going to be perpendicular to the equipotential surfaces. If there is any component in this direction, then it will not be an equipotential surface, because there will be E dot dl existing in this along the surface. So if there is no tangential component, only then it will be an equipotential surface. So you see, electric field lines are perpendicular to equipotential surfaces. Now there is one more thing I need to tell you, where some students are a little confused. I have told you that E as well as F as well as phi follow the superposition principle. but the concept or the representation through field lines does not follow superposition. You can clearly see that this plus charge and this plus charge is going to create field like this, and I want to represent field line like this. So it will be difficult to use superposition and draw these lines. However, we can draw these lines by finding the equation of these lines from equipotential surfaces, and it will be easier to draw these lines. Otherwise, superposition principle is not going to give us the correct answer. So while representing using electric field lines, we are not able to directly use the principle of superposition in drawing the electric field lines. So in that sense, this superposition principle is quite not applicable directly while we represent through field lines. So this is one important thing which we should remember.